Hi, my name is Jeff Gabala. I'm an engineer here at Corey Micronics, and today in this video we're going to talk about the different types of amplifiers that we offer, and also some of the key operating parameters to consider when choosing an amplifier. The amplifiers that we offer range anywhere from tens of watts of output power to hundreds of watts of output power, and low noise amplifiers that range from milliwatts of output power to hundreds of milliwatts of output power. So some of the key specifications to consider when choosing an amplifier are the gain, the operating frequency range, the output power level, the efficiency, the linearity, and the noise of the amplifier. The amplifier gain is a measure of how much the amplifier will increase the signal level at its output. It's the ratio of the amplifier's output power to the amplifier's input power, and it's measured in dB. The amplifiers that we have here at Corey Micronics range in gain from 30 dB to 50 dB. This high gain allows you to use a low-level signal source like a software-defined radio or a off-the-shelf signal generator that outputs milliwatts of power and generate tens or hundreds of watts of power. In a low noise amplifier, the gain, high gain will improve your overall system noise figure. The operating frequency is pretty straightforward, and it's it tells you what RF frequencies that the amplifier will amplify and maintain its operating parameters. It's the high frequency and the low frequency that the amplifier will maintain its operating parameters. The output power level is pretty straightforward as well, but it can be measured a lot of different ways. One way to measure output power is saturated output power. And the saturated output power is the absolute maximum power that you could get out of the amplifier. Basically, if the amplifier is operating at saturated output power, if you increase the signal level, the output power will not increase. It appears as if the gain of the amplifier has decreased. The 1 dB compression point is another way to specify the amplifier's output power. And that is the point at which the amplifier's gain has decreased by 1 dB from some lower level output power. So for instance, if you had an amplifier that had 10 dB of gain with 1 watt of output power, and then had 9 dB of gain at 10 watts of output power, that would be the 1 dB compression point would be 10 watts of output power, because the gain is decreased by 1 dB at 10 watts. Another way to specify the gain is with a very specific type of signal operating at a certain set of parameters. So you could specify the amplifier as a 10-watt amplifier with a LTE signal and 10 watts of air vector magnitude. It's very likely that the amplifier will put out more than 10 watts, but the EVM would not be at 10% anymore. It would get worse. Here at Corey Micronics, we use all of those different methods to specify the amplifier's output power, and which specific way we use really depends upon the application that the amplifier is meant for. The next thing to consider about an amplifier is the efficiency. The efficiency is the ratio of the amplifier's RF output power to the amount of power that the amplifier is pulling from its power source. So if you had an amplifier that was 100% efficient, all the power that was coming from the power source would be delivered to the load as RF energy. Now, 100% efficiency isn't possible, so that difference in efficiency from 100% is generating heat in the amplifier. So if you had a amplifier that was 50% efficient, and was a 10-watt amplifier, it would take 20 watts in to output 10 watts, and that additional 10 watts is lost in the amplifier and generates heat. You have to remove this heat from the amplifier to maintain a safe operating condition and not damage the amplifier. Typically, the most common way to remove the heat is through the use of heat sinks or fans. We have experience here at Corey Micronics in cooling amplifiers, and we can assist you with properly sizing heat sinks and fans to cool the amplifiers in your application. We can even package up our amplifiers, our modules. A module is what you see here. We can package these up and include heat sinks with them and fans and put them in enclosures for a rack mount unit or a benchtop unit, or we can assist you in choosing those heat sinks and fans, and you can package it up yourself. The next thing to consider is amplifier linearity. And linearity is something that might be important to you and or may not be important, or could be the most important thing. It really depends on your application. If you're amplifying a constant amplitude signal, you probably don't care much about linearity. But if you are amplifying an AM modulated or vector modulated signal, then linearity is probably pretty important. If amplifier's linearity is inadequate, your output signal will be distorted and noise will be added to it. And these degradations can impact your system bit error rate and cause bit errors. You can use the 1 dB compression point is a parameter that can indicate linearity and tell you when the amplifier is starting to become nonlinear. You can then use that information to understand what the amplifier might do with your signal. So, knowing your power level, your signal characteristics, and your amplifier's 1 dB compression point, you can gauge what kind of power you could expect out of your amplifier with your signal type. Third order intercept point is another parameter that provides a linearity measurement. That represents the level of third order intermodulation products that are generated by the amplifier. If these intermodulation product levels get too high, they act as noise on your output signal, and if they get too high, they again will degrade your system BER. EVM is another method to measure linearity, and that's probably the best way to gauge the linearity for like a vector modulated signal like LTE or WCDMA. The vector modulated signals can have very high peak to average power ratios, maybe 10 dB or higher, which would say that your amplifier might have to output a signal that's 10 times in power as to what the average power that it's putting out. And these types of signals can put a strain on the amplifier. The best way to deal with these types of signals is with an amplifier architecture like Doherty, and to incorporate linearity correction. These architectures will allow you to maintain amplifier efficiency and be cost effective. If you could also oversize your amplifier to handle these very high peak powers of those types of signals, but that would be costly and inefficient. The best way to gauge your amplifier's linearity is with the signal that you plan to use at the right power level. But if you only have 1 dB compression point and saturated power, you can use those to gauge what kind of power you can get out of the amplifier, and knowing your signal characteristics, you can predict what the amplifier might do with your signal, and then you can follow that up with testing. Here at Corey Micronics, we have the capabilities to measure the error vector magnitude of the advanced signals like LTE and WCDMA, and we can help you characterize our amplifier specifically with your signal type so that you can be sure that it works properly. And the last spec to talk about is noise figure. Any amplifier will add noise to the signal that goes through it. So the noise level out of the amplifier is going to be higher than the noise level into the amplifier. And the noise level will be increased by more than just the gain of the amplifier. And that amount, that extra amount that the noise level is increased by is called the noise figure. Typically for power amplifiers, noise figure is not that critical because they are amplifying, dealing with really high level signals. It can be critical if it's in a system where the power amplifier output might leak back into a sensitive receiver, and it could degrade your receiver sensitivity. But the noise figure is most important for low noise amps. These amplifiers deal with really low signal levels. You're trying to maximize your sensitivity. So a low noise amplifier won't put out a lot of power, but it will have a lot of gain and not add a lot of noise to the signal output. Typically, a low noise amplifier will have a sub 1 dB to a few dB noise figure, where a power amplifier might have 10 dB or higher. A lower noise figure in your LNA is going to make your overall system sensitivity for your receiver better. So, we've got a lot of variety of amplifiers here at Corey Micronics available as both modules, or we can package them up into enclosures, into integrated systems, and integrate them with our other products like filters and diplexers. You can check out our products on our website. That's www.cormic.com. Please have a look and contact us with any questions or extra information you need. We're happy to help. Thanks for watching.